In this video, I'm going to give you a mini lecture on quadratic equations. So this won't be an in-depth lesson on everything about quadratic equations, but it'll give you a good idea of what you're supposed to learn in this section. I'm going to give you a quick look at a few examples from each of the things that you're going to be expected to learn. So let's look at them. We're going to talk about what quadratic equations are, what we can do with them, and solving methods, as well as strategies that go along with that, and this thing called the discriminant and what it's used for. So what are quadratic functions, or excuse me, what are quadratic equations, first of all, because that's what this section is really about. And we're also going to talk about quadratic functions, which you will encounter later in the course, so I'll be connecting some of the dots as we go along here. But the main objective in this section is solving quadratic equations. So what is a quadratic equation? Well, a quadratic equation in one variable would look like this, where you just see x is the only variable. The a, the b, and the c represent constants that don't change or vary. So the only thing that changes from problem to problem, or that is unknown from problem to problem is what I should really say, is the x. Whenever you get these things, you're solving for x because it's the only thing that we don't know. We also have an example here to show you what that would look like with actual numbers instead of a, b, and c. So here's the example, 6x squared plus 7x minus 3 equals 0. That's an example of a quadratic equation in one variable. Then we have a quadratic equation in two variables would look like this. Now, how is this different from what's up here? Well, instead of a 0, you have y, which is a second variable. And when you have a second variable, then you can graph the equation on an xy plane. So for example, if you had y equals 6x squared plus 7x minus 3, the only difference from up here again is that y is in place of the 0. So that means instead of just saying that the output has to be 0 and solving for x in that one case, you're letting y be allowed to be many different things. Then we have functions. So a quadratic function would look almost identical to the equation in two variables, except now instead of y, I have a different notation, f of x, which means function of x. So this is where we've decided to replace the y with this notation, which means that we're saying that the output depends specifically on what x is. So in other words, x is what's chosen first, and then we consider the y value the result. So an example of this, of course, could be that same polynomial again, but instead of y, we have f of x. Now, what can we do with these things? Well, we can solve them. So if it's an equation, like the first example I showed you that had just a number on the opposite side of the equals, then you can solve for the one missing variable. You can evaluate functions, which means you can plug in a value for x and find out what the value of y is, or the value of f of x. You can graph functions or equations in two variables. So the things that you really have to worry about learning right now are solving equations, but I will just be talking a little bit about these other items as we go along. So solving quadratic equations, there are a few different methods you're going to need to learn. The zero factor property, this is where you actually factor the square root property, where you'll be taking the square root of both sides of the equation. And sometimes completing the square is needed in order to be able to use the square root property. And the quadratic formula. So you probably memorized that back in high school or the last time you saw math. Now, let's look at each one of these. The zero factor property. Now, before I get into each one of these, let me just say, students often wonder, well, why do you have to teach me different methods of solving the same type of problem? It's not just to give you more stuff to learn. It's so that you can increase your toolbox, or you can stock your toolbox, because some problems will be easiest to solve with the zero factor property. Others would be easiest with the square root property, and still others might be best solved with the formula. So think of them as tools for your toolbox. So the first tool here is the zero factor property. So as the name implies, you will be factoring, which is undoing multiplication. And 0 implies that you're going to have factors that you set equal to 0. It's based on this truth that when you multiply two items and you get an answer or a product of 0, that means either A had to be 0 or B had to be 0 or possibly both. So we can use that to our advantage with quadratic equations. So here's an example using the zero factor property. So here we have the equation 6x squared plus 7x minus 3 equals 0. And we want to know what the x value is that would make this statement true. We want to solve it. We want to find a solution to make it true. So we can factor this, and if you remember multiplying two sets of binomials together to get something that looks like this, what you're doing is that in reverse, and you may know that as foiling. First, outer, inner, last is how you would multiply them, so we're unfoiling. And the method that I like to teach students is the AC method. That's where you take the first coefficient and the last coefficient and you multiply them together, and then you try to find something that multiplies to that number and adds up to the middle coefficient. So we're going to multiply 6 times negative 3, and that will give us negative 18. So I'm looking for two numbers that multiply to give me negative 18, and also when I add them, they give me this positive 7 in the middle. And what I want to do is rewrite that middle term into two pieces. So start thinking about all the different ways you know how to multiply two numbers to get negative 18. So you might start with negative 1 times 18, and that would give you a difference of, let's see, negative 1 plus 18 would give me a difference of negative 17. Now that does not match what's here. I want a positive 7. So that didn't work. So maybe we could try, how about negative 2 times positive 9? And when I add those together, I do get positive 7. So that's the route I want to go. So what I'm going to do is I'm going to rewrite the middle term. See, I've just taken this 7x and I've rewritten it into the two pieces, two terms, one with the negative 2 as a coefficient and one with the positive 9 as a coefficient. Now that I have that stretched out, I can group these items together. So I'm going to group these two terms together and these two terms together. I'm going to look at each set individually and see what I can factor out that's common. So from the first set, I was able to factor out a 2x, leaving 3x minus 1 in the parentheses. Okay, and if you multiply the 2x back and distribute it, you'll get 6x squared and negative 2x. From the second set, I noticed that 3 was common, so I factored that out, and that left 3x minus 1 inside the parentheses. And just to do a quick check, 3 times 3x would give me 9x, 3 times negative 1 would give me negative 3. All right, so now we're getting closer. Here at this step, we want to just notice that the bubble here with the parentheses in each of these is identical, right? If it's not, something went wrong, you got to go back and fix it. Or it could not, it might be one that's not factorable. That happens sometimes. All right, now I've taken the 3x minus 1 factor quantity that was common to both of these chunks, and we've taken that out as the common factor, leaving in its place the 2x here is now part of a second set of parentheses, and the 3 here, positive 3. Okay, so now I've got my polynomial factored. My quadratic, the left side of my quadratic equation is factored. So now that I have that, I have this whole piece right here times this second piece here equals 0. So that means either this blue piece was equal to 0, this green piece is equal to 0, or possibly both. So that's how I'm going to find my answers that will satisfy the equation. So I take each factor, set it equal to 0, and continue to solve, okay, until I get my 2 answers. Then you plug them back into the original equation and make sure that you do them one by one, not both at the same time. Take 1/3, plug it in to both the x, anywhere you see an x, simplify and make sure it equals 0. Do the same with this one. All right, now let's do another example. This time we're going to look at how, when it would be appropriate to use the square root property. So this is our second tool. And we may need to do some completing the square for a few of the examples we're about to look at. So the square root property says if, now remember, I always tell students that algebra and any other math class is an if-then course. If certain things are true, then there are these tools at your disposal, or then you can do something else, right? You always have to ask, well, what are the conditions first? And that will lead you to your solution, your way of solving the problem. All right, now if x squared is equal to some number k, then it must be true that the square root of x squared, just plain x without a square on it, would be equal to the square root of k, or maybe even negative the square root of k. And we'll see why that makes sense here. Let's look at an example with actual numbers. Solve using the square root method, and here's our equation. Okay, well, you might be able to look at this and just know that something squared equals 25. I know that number should be 5 because 5 times 5 is equal to 25. But isn't it also true that negative 5 times negative 5 would give you positive 25 as well? So that's the reason that we always have both the positive and the negative possible solutions. So that's why the answer for x could be negative 5 or positive 5 here. Now what about this one? This is more complicated. Instead of just an x over here, we have a whole quantity with an x inside it. So the answer is not as clear. So you might still be thinking, well, I know whatever is in this set of parentheses here, that has to be 5 or negative 5, but that doesn't mean the x is 5 or negative 5, right? So what we do is we take the inside part. Basically, you're taking the square root of both sides. That cancels out the square here, and you're left with x minus 3 is equal to the positive square root of 25, or x minus 3 is equal to negative the square root of 25. And then you have to continue solving from there. If you add 3 to both sides, you're going to get x is equal to 3 plus 5, or x is equal to 3 minus 5. And so you get your two possible solutions, either x equals 8 or x equals negative 2, and just plug each one in individually and make sure they satisfy the equation. Now here's another one. Now this one is not in the form with a quantity and a square on the outside. It's got other terms that are not squared. So you have to approach this totally differently. But if you recognize this pattern here, which is a perfect square trinomial, then you can rewrite it in the form you want. So what I mean is, notice that the square root of 9 is 3. And if you double 3, you get 6. So what that means is I can rewrite it like this. X minus 3 quantity squared equals 25. And if you just try this out on the side here, you'll see that that is correct. It actually works. If I just do x minus 3 times x minus 3 and FOIL it out, and I would get x squared for my first two terms, negative 3x, then negative 3x, and then positive 9. And so then what do I get? I get these together give me negative 6x plus 9, right? So it works. And I was able to know that just by looking at it, and I recognize the pattern. The square root of this one is the double of this one. And then you just make sure to keep the sign of the middle term in there. Now that we've rewritten it this way, we're back to this problem, right? So we're going to do the same steps again to get the answers. Same answers. All right, now let's look at, we just did this one. We're still going to have all the same steps and answers as the last one. Let's look at this one now. This one's quite different. Notice that there is no quantity with a power of 2 on the outside. Also, we don't have 3 terms, so it doesn't fit the pattern to be able to rewrite this as a binomial squared. But what I can do is I can force it to be a perfect square trinomial so that I can rewrite it the way I want it. And this method is called completing the square. So this is an example in which we need to complete the square first, right? So you're going to force it to be a perfect square. We don't always have to do that. Notice in the other problems, they were already perfect squares, so we just had to make sure they were written in the right way and we were good. Now we're going to have to do some extra stuff here, but it's not so bad. All we have to do is we have to come in here and we have to make some space for that third term so that we can have a complete perfect square trinomial. And whatever we add on this side, we just can, well, we can add anything we want over here as long as we also add it over here and keep everything balanced on the other side. So what do we need to add? Well, remember before we had something here, and whatever its square root was, then you double that and you get the middle term. So if we work in reverse of that thinking, we want half of this one would be 3. And then if I square 3, I'll get 9. So what I need to do is add in 9 there. I'm going to add 9 on both sides. And another way of saying adding 9 is I'm adding 3 squared, right? So now I have a perfect square trinomial, which I can rewrite as a binomial squared. And we notice that 16 plus 9 became 25. And I'm back to that same problem again that we solved earlier. Let's look at another example. So now we've talked about how to use the zero factor property. That was our first tool. The second tool was the square root method, which sometimes requires an adapter piece, which is completing the square. So let me just go back to this, just to review what we've done so far. Zero factor property, square root property with the sometimes needing a converter or an adapter of completing the square. And now we're looking at the third tool, which is the quadratic formula. Right, the quadratic formula. Do you guys remember what that looks like? Hopefully you've memorized it right here. X equals negative b plus or minus the square root of b squared minus 4ac over 2a, all over 2a. Now your teacher may have had a song to help you remember that, so good on you if you remember it. If you don't, then memorize it or put it on your index card for the test. But I would advise you to definitely memorize it. It comes in very handy throughout any mathematical things you might ever have to do. So just keep it in your back pocket. And notice that I have in pink here, it says if ax squared plus bx plus c equals 0, then you can use this. Again, it's an if-then course. You have to have your quadratic equation in this form to be able to use this formula. Now this one is in the correct form. Notice it's set equal to 0. We do have x to the power of 2 on here, so it works with this tool. Now let's start identifying the pieces. First thing to do is to identify a, b, and c as they are in this equation. A is in front of the x squared term, b is in front of the x term, and c is the coefficient of the constant term. So here, I don't see anything in front of the x squared term. What that means, the number is just 1. So we're going to go ahead and use 1 as the first value that we're going to be plugging into the formula. B is -6, and C is -16. So now I have the formula rewritten here, and I'm just going to come in and start replacing each thing, each letter, with the values that are assigned to them. So let's start with -b, and I'm going to put in the value of b, which is -6. Now, because I have a double negative here, a negative times a negative becomes a positive. So I'm just going to get rid of that. Now here's another b. I'm going to replace that with the negative. So I'm going to put parentheses, since I know that b, the whole quantity of b has to be squared. And b happens to be a negative here, so I want to make sure the negative gets squared as well. Okay. And then I'm going to replace the a with the a and the c. So let's go ahead and put those in. We're going to do 4 times 1 times -16. And then underneath, we can replace the a here also with 1. Fix our 4 here. It got a little bit erased. Okay, now we just simplify. Okay, so let's go through this. What can we simplify? Well, from the top down, I see -6 squared is -6 times -6, so that would be +36. And then -4 times +1 is still just -4. And -4 times -16 would be +64. So I'm going to replace that with +64. And down in the bottom, 2 times 1 is simply 2. Can we replace anything else or simplify anything else? How about 36 plus 64? That together would be 100. Okay, and still I can simplify this more because I have the square root of 100, and that is equal to 10. So now I have 6 plus or minus 10 over 2. So let's split that up, because the plus minus sign, if that throws you off at all, just think of it this way. The plus minus sign right here, all it means is that you're going to do both, one at a time. So we have x is equal to 6 minus 10 all over 2, or x equals 6 plus 10 all over 2. And then simplifying each of those, we'll get 6 minus 10 is -4, so -4 over 2 gives you -2 as one answer. And then 6 plus 10 is 16 over 2. 16 over 2 is 8. So now we have our two solutions. So that's how we do the quadratic formula. Now the last thing on our list to discuss in this section is this thing called the discriminant. And the discriminant is simply the part underneath the radical of the quadratic equation. So it's just this piece right here. This is the discriminant, only the stuff underneath the square root. And the reason it matters is because it comes right after the plus minus, and it's underneath the square root. So a lot depends on what the sign of this and what the value of this part of it is. Because if it's 0, then the whole square root part goes away along with the need for the plus minus, and you just have one answer, which is -b over 2a. If your sign is negative, also when you simplify all this, if you get a negative result, well, you can't take the square root of a negative, and you get an imaginary number. So then you have you have two non-real answers, which wouldn't show up if you were doing graphing. It wouldn't show up on the XY plane. So that's pretty cool that you can tell a lot about what to expect about the graph by just looking at this. So now let's fill out this table, but before we do, we're going to do a few different examples so that when we're filling this out, we have some context and we understand what it means. So here's one example. Calculate the discriminant, then use it to determine the number of distinct, that means solutions that are not the same, and tell whether they are rational, irrational, or non-real complex. So let's break it down. What does rational mean? It means that it simplifies and there's no more square roots left in it. Irrational means you're going to have a square root somewhere still that you can't simplify any further. It's not a perfect square. And non-real means there's an I in it. Remember, I is the square root of -1. So non-real would be any ones that have negatives under the square root. Okay, so for these problems, all we're asked to do is calculate the discriminant because we want to just talk about the types of solutions that we should expect as our final answers. All right, so the discriminant is b squared minus 4ac. So let's calculate that. So we're going to do, I'm going to come in here and do it here. I'm going to do b squared, which is b is 2 here. So what's 2 squared? 2 squared is 4, right? B squared minus 4 times a, which is 5 here, and times c, which is -4. Okay, so we're going to simplify this. Right? -4 times 5 is -20. -20 times -4 is +80. So 4 plus 80 is 84. And what we have is a positive answer. That means that there's going to be a positive after the plus minus. There's going to be the square root will be a real number. So we're going to have 2 real numbers after the plus minus, which causes us to have 2 separate answers for x. So let's go back to that table we were looking at. If we have a positive number as the discriminant, then we're going to have 2 solutions, 2 distinct answers for x, 2 different answers. Okay, now what about for this column? It says type of solutions. Remember what we had to choose from was rational, which means no square roots in it, irrational, which means square roots that don't simplify, and then non-real, right? Well, we know they're going to be real because we already saw that there's a positive underneath the square root, so it's not going to be imaginary. But are they going to be rational real or irrational real? Now, if it's a perfect square, so for instance, here we had 84, right? Well, that's not a perfect square. If I take the square root of 84, I'm not going to get a regular integer. The 2 perfect squares that this is sandwiched between are 81 and 100 are the 2 perfect squares that have the square root of 9 and 10. So in between that, it's not a perfect square, it's a rational. So because it's a not perfect square, we had 2 irrational real number answer solutions, real and irrational. Now, if it had been a perfect square, say 81, then we would have 2 real rational answers. So the answer to this one, because it said calculate the discriminant, then use it to determine the number of distinct solutions and tell whether they are rational, irrational, or complex, then my answers are going to be, my actual answer to the question is 2 real rational solutions. Okay, so that's my answer. Now I have more stuff down here, but I'm not gonna, well, actually, yeah, I'll go ahead and show it. Now, what if we turned this into a function and we wanted to graph it? Well, this is what it would look like. And notice that both here and here are places where y equals 0, because this is your y-axis here and this is your x-axis here. So if you find the coordinates for those values, what are they? They are, what does it look like? Close to 1, 2, 3, 4, 5. I don't even know what that x value is. It's not perfectly on an intersection, but it's something less than 1. But let's ignore x for a moment. What we want to know is what is the y value. The y value would have to be 0 because it's on the x-axis. I haven't moved up or down. And same thing here. I have another x value, so x1 and x2, comma 0. And what would those answers be? What would these x values be? How can you figure out what they are? Well, you just complete the rest of this formula, and then you'll know the x values that go in each of those. And that's why they don't fall on a perfect intersection, because they're irrational, right? With the square root of 84, there's going to be a square root that does not simplify. Let's look at another example. If I have x squared minus 10x plus 25, what would the discriminant be? Okay, so again, we're going to just do the discriminant right here. We'll do b squared minus 4ac. So b is negative 10. Negative 10 squared would be 100. Then minus 4ac, minus 4ac. So what is a and what is c? A is 1 and c is 25. So 1 times 25 is 25. 4 times 25, or negative 4 times 25 rather, is negative 100. So what do we get? 100 minus 100 equals 0. And now, if I put a 0 underneath this square root, then the square root of 0 is 0. So that makes the plus minus part disappear, because it doesn't matter plus and minus 0. So then what we figure out is we only get one solution for this, right? And since there's nothing left underneath the square root, there's nothing, the square roots are all going to go away, so it's rational, right? So we're going to get one rational, real solution. Now let's look at what that would look like if it was turned into a function and graphed. Look at that. This is your x-axis, and it's only touching one spot. That's where y equals 0. It only does it at x equals 5. So if we were to continue working out this whole equation formula, we would get that x equals 5, and that would be our only answer. All right, let's look at one more. Here we'll do the discriminant again. So we want b squared minus 4ac. So b squared, what is b? b is negative 1. Negative 1 times negative 1 is positive 1. Then minus 4ac. Well, what is a and what is c? A is 2, c is 1. 2 times 1 is 2. Then negative 4 times 2 is negative 8. And 1 minus 8 is negative 7. Ooh, we get a negative underneath the square root. So if we have a negative underneath the square root, then we get an imaginary answer, or a non-real answer. Also, 7 is not a perfect square. So we're going to get, well, I guess we don't even really need to define it past just saying that it's non-real. We're going to have two non-real, complex, and irrational, but you don't usually have to say that, answers. Okay, irrational kind of is reserved for answers that are not imaginary. So we have two non-real complex answers, or solutions, you could say, okay? Now, if we were going to try to turn this into a function, instead of just making it only equal to 0, if we wanted to let it be a function of x and graph it, what would that look like? Okay, notice that here's my x-axis, and this thing is not touching it. So there's no time that you're ever on this parabola that you would actually be touching the x-axis. So there's no time that y is ever equal to 0 on any of these coordinates that are ordered pairs that you could find anywhere along here. So there's no solution to this, right? So that's, or no real solution, I should say, no real answer solution, but there are non-real, imaginary solutions for it. So back to our table here, we found that with 0, we had only one real rational solution since all the square roots went away. And We also have, if it's negative, two distinct solutions, but they are non-real. So what did we just learn? What is the discriminant? What is it good for? Well, we know it's the part underneath the square root in the quadratic formula, b squared minus 4ac. But why is it useful? Well, if you're talking about just an equation in one variable, well, then you'll know how many answers to expect and whether they should have square roots in them, right? So some of the answers when you use the quadratic formula, the square roots won't simplify. And sometimes you wonder if you made a mistake somewhere. And so kind of knowing this up front is sometimes helpful. How is it useful beyond that? Well, later on, when you start dealing with equations in two variables and start graphing things, or a function, then the same is still true. You can still figure out how many answers you should have when you're looking for zeros of the function. So when you set the y value equal to 0 or the function value equal to 0, and then you solve for x, you're finding the zeros of the function. And what are the zeros of the function? How are they useful when graphing? They're also called x-intercepts because whenever y is 0, you stay on the x-axis. And it's very useful to know where a graph is going to be touching or crossing the x-axis when you're trying to graph something. So super useful when you get to the graphing section of this course with quadratic equations. All right, so that's everything we need to cover. I know you probably want more examples, and that's why you have your worksheets with coordinated videos to work out. But for this, I wanted you to see what are quadratic equations. Okay, we saw different examples. We also know that they can be graphed later on in the course, and they look like U-shapes called parabolas. And we can do different things with them. We can solve them. We can later in the course graph them, and we can use the discriminant to tell what kind of solutions we're going to have. What are the different solving methods and strategies? The three to remember are how to use the zero factor property, how to use the square root property, how to complete the square if you need to adapt it so that you can use the square root property, and of course the quadratic formula, which by the way works in every single case, right? The zero factor property, you have to have something that factors, and the square root property, you have to have something that is a perfect square, so you can take the square root of both sides. But the quadratic formula works no matter what. Of course, that is as long as the equation is set equal to 0 first. And the same is true for the zero factor property. Your equation has to be set equal to 0 first. So don't be fooled when you see a question. You could see the same problem, and instead of it being written like this, maybe it was written like this with the 3 on the other side of the equal and an opposite sign. So you would have to realize before you start trying to factor anything, you need to move that over to the other side and change the sign and make this a 0 here. Or at times you might not notice it because perhaps there could be something here like maybe a 5 and a -2, say over here. And some students will completely miss the fact that there's not a 0 on this side, and they'll just start trying to factor this portion of it, when really what you needed to do was first add 2 to both sides so that you could then proceed with the problem. So in any case, if you're going to do factoring or if you're going to do the quadratic formula, you're going to need to set it equal to 0 first. All right, so I'll close with that and see you in the next video.